Welcome to the online causal inference seminar. Today, we're excited to have Qingyuan Zhao from Cambridge University, who will talk about selection bias in 2020. In Q&A, we have Phyllis Yu, who will be happy to answer all your questions. Qingyuan Zhao will also stop from time to time to take questions from the audience. After the talk, we'll have a discussion by Louisa from Harvard University. Questions today will be handled by Michael. I'm switching over to him now.
Thank you, Dominic. So as Dominic said, we're very lucky to have Phyllis Yu today, who will help with questions on the first half of the talk. So please submit your questions through Q&A, and we may provide some questions to Qingyuan live, in which case, if we select your question, we'll reach out to you and ask you to raise your hand and unmute yourself. So with that, I'll switch it over to Qingyuan, who please start when you're ready.
Can everyone hear me and see my screen share okay? Great.
Yes.
Well, so today I'm going to talk about some selection bias problems I've encountered with in 2020. Right, so selection bias is really a very general umbrella term. So these are two definitions I've found. In Cambridge Dictionary of Statistics, it says selection bias is the bias basically whenever incurred whenever a treatment is chosen by the individual involved or is subject to constraints that go unobserved by the researcher. It's a very general definition. If you look at Wikipedia, it says it's the bias introduced by a selection of individuals, groups, or data for analysis in such a way that proper randomization is not achieved. It's a little bit strange, actually. This definition somehow emphasizes proper randomization, and it's a little bit perhaps different from what we know selection bias otherwise. But very interestingly, the Wikipedia article collects many types of selection bias. They have a bunch of names. I'm not going to go through all of them, because basically what happens is if in certain types of problem, ignoring something would give you a selection bias, then people give it a name, and then that name gets to sort of propagate it through the literature, and then you get all these different kinds of names for potentially quite different reasons of selection bias. But before 2020, I always thought selection bias is, well, obviously important, but maybe not very, very common in practice. I don't remember taking any course that involved more than one lectures about selection bias. It's sort of one of those things that the lecturers mentioned in some of the lectures. They say, well, if you do a model selection, then you cannot use the same data to make inference for the model you selected, things like that. But never really had a sort of a particularly sort of real experience with selection bias. One confusion I had about selection bias is in consulting sessions, clients, they often come in and they want to know how to interpret the results. And they show me their analysis, which is usually an array of data processing and model selection. So it's a lot of sort of data science things going on. But then they want to interpret the results. And often they want to know, does this statistical test tell me what I want to know? But because of the very complicated data processing and model selection they do, it's actually not very easy to say, for me as a rigorous statistician, to say how to interpret their results exactly. So I always got a little bit confused and fuzzy when clients ask those questions. I want to tell them, you're not doing the entirely rigorous statistical analysis, so I'm not sure how to interpret your results, but I also recognize that there doing something that makes a lot of sense to them, and they are seeing sort of signals that they kind of expect, and they want to be able to attach some rigorous meanings. And I've seen many anecdotes about selection bias, but I always thought they are far away from me. I'm a statistician and I work in fairly ideal settings most of the time. And I think there are a lot of smart people who are applying statistical methods in all kinds of problems. So they also learned all these things about selection bias, just probably as much as I did. So the practice cannot be that bad, right? But my experiences in 2020 totally changed my perspective. And I kind of, after 2020, I have like a little bit of existential crisis, not just from the pandemic, but also just seeing all the sort of a lot of the applied work, and started to wondering where, as a field, we're going, and what, like, how do we actually contribute to the scientific community as statisticians, epidemiologists, social scientists, data scientists, or just general people who work with data? How do we make a positive contribution to the society? So I'm going to talk about two topical examples that led to this existential crisis. The first is about some initial estimates of the COVID-19's infectiousness and incubation period. It's based on a paper that I co-authored with Phyllis, Sergio Bacalado, and Rajan Shah. It's accepted at Annals of Applied Statistics. The second example is about racial bias in policing. As you know, this is also a very controversial topic, and we were motivated by some recent debates, and the talk will be about a short note we wrote on this problem. Just before I start, there are many people who have offered very generous help and suggestions in these projects. These are very recent papers as well. They're written in this year. So let me know if you have any comments and suggestions. All right, so the first problem is about COVID-19. So many of these COVID-19 studies were based on exported cases from Wuhan, because Wuhan was originally the center of the epidemic, and most of the initial cases are related to Wuhan. They're either residents in Wuhan or they traveled from Wuhan to other places in China and in the world. So a lot of the initial COVID-19 studies were based on information about these exported cases. These studies are extremely influential just because of how early they were written. They have thousands of citations by now already, and they were sort of really important in the initial responses to COVID-19. So that is our basically determined our initial understanding of this new infectious disease. So in the paper, we listed many types of selection bias that are commonly incurred in these studies: under assortment, non-random sample selection, right truncation, and sometimes these studies ignore travel restrictions and the fast epidemic growth. But basically, those are just sort of names for different kinds of selection bias. But I think the common mistake that a lot of people are making in these studies is that people tend to sort of think in this way, that we have some new data collected for this new infectious disease, and we have all these existing models. Could be a statistical model, could be an infectious disease differential equation model, and then they just try to put these things together. So they fit the existing model with the new data, and then they get some new results, and they conclude that this would apply to this new infectious disease. What researchers don't often realize is that each infectious disease probably has its own sort of different characteristics, and the data collected for each infectious disease are not always the same. So they may have different structures, and they may have been collected under different circumstances. And that means that you may not be able to directly apply some existing model. So I'm gonna give you an example, but before that, let me just briefly tell you this data set that we collected, which I'll use to illustrate some of the mistakes that have been made. So this data set is collects about 1460 COVID-19 cases in 14 locations that are in this plot. So most of them are other cities in China. There are also several international locations that are just Asian countries and regions. So these are basically, these 1460 cases are all the cases confirmed in these locations by the end of February. And among these cases, there are 378 exported cases from Wuhan. And here is what the data look like. So it turns out that a lot of these health authorities, they publish very detailed information about each confirmed cases. So they tell you, for example, where the case lives, the gender, the age, whether they had known epidemiological contact with others, and if so, who are the epidemiological contacts. And they tell you a lot about sort of the travel history of this person. When did they go into Wuhan? When did they leave Wuhan? When did they go to the hospital and get isolated? And when did they show symptoms? When did they get confirmed with the PCR test? So a lot of information actually that's already there in the epidemiological case reports. But for most of the initial studies, people often just use this single number, this single date of symptom onset, and try to sort of form a epidemic curve using this single column. But actually, there are a lot of useful information for us if we want to do a more detailed analysis. Two other very important variables is the beginning of stay in Wuhan and the end of stay in Wuhan, which gives you a time interval for this person to be exposed, when they were exposed to COVID-19. So let me first tell you a naive method and why it underestimated the growth of COVID-19 by a lot. So this method is published in, I think, in the Lancet on January 29th this year. And what they did is it's a basic so-called SEIR model. So it has sort of 4 compartments for susceptible, exposed, infectious, and recovered populations. And this model is a differential equation model for how these 4 populations are changing over time. So this model is used for the epidemic inside Wuhan. And then they use the Poisson process to model case exportation. What's, I think, really astonishing to me was that they actually fitted the model with this model using just 17 cases. These are the international cases who showed symptoms before January 20th, 2020. If you read the results of the initial studies, it actually gives you a very tight confidence interval of the R0. and the initial doubling time with just this 17 international cases. So it's a little bit unbelievable to see how they were able to fit a very accurate model with just 17 cases. But I did a replication of their analysis. And instead of using a more complicated differential equation model and a Poisson process observation model, I just fitted some Poisson log linear model. So essentially, this shows you what I did. So each data point is the number of cases who showed symptoms on that day. Okay, and then I simply just fitted a Poisson log linear model, assuming that the mean of the count is growing exponentially. And then the observation we actually observe follows a Poisson distribution with that mean. So I fitted two models. The blue curve is trying to replicate the original analysis. This used symptom onsets before January 20th. So that is this dashed line. And I got the coefficient from the Poisson log linear model, and then I translated that coefficient, that slope coefficient, to the doubling time. And it turns out that the doubling time is about 5.9 days, and the 95% confidence interval is 3.4 to 15.7. So it's a very inaccurate estimate. But if you look at this blue curve, it does not seem to fit the next few days, the data from the next few days very well. So it may be reasonable to extend this the data we use a little bit and consider using all the symptom onsets before January 24. So that is this red curve, and it seems to provide a better fit to the case counts. And if you examine the cumulative sum of the exported cases and taking a log, you see that this red line also seems to fit the data pretty well. And this red line corresponds to a doubling time of 3.9 days and a confidence interval of 2.9 to 5.4, sorry, 5.5. And well, this is the original study. The results of the original study is doubling time is 6.4, so it's not very far away from our initial estimate, but they got a very, very narrow confidence interval for reasons that I don't understand. Okay, so although this seems to be providing a reasonable fit to the data, these models still have two problems. The first problem is they do not take into account Wuhan's travel ban on January 23. So basically after January 23, nobody can come out of this city. And they also ignore the rich information that I showed you earlier that is available for each individual case. So let me try to build a model from the first principles. So for these exported cases, they have four crucial epidemiological events. So there's the beginning of stay in Wuhan and the end of stay in Wuhan, which define a time interval that the person is exposed to the new coronavirus. Then there's the time of transmission. The person is infected with this new virus, and this is, of course, unobserved. And then there's the time of symptom onset. So what I'll do below is I'll define the support for these four variables, B, E, T, and S. I'll then construct a generative model for these four variables. Then I'll define what kind of sample we can observe from this population. And then I'll derive some likelihood functions to adjust for the sample selection. So this is sort of just following the basic principles of statistical inference. So The Wuhan-exposed population is basically all the people who stayed in Wuhan during this beginning of this initial phase of the epidemic. So we defined it as anyone who stayed between December 1st and January 24th. And January 24th will be called time L, it's the time of the lockdown. There's some conventions just to convert this practical problem into a mathematical problem. B equals to 0 means they've stayed in Wuhan before time 0. So they are basically residents of Wuhan. E is infinity means that they did not arrive in any one of those 14 locations we're considering before this time L. T is infinity means that they were not infected during their stay in Wuhan. And S equals to infinity means that they did not show symptoms of COVID-19. So this means that the population, the Wuhan-exposed population, can be described as this set P, that is all the B, E, T, and S that satisfy these constraints. So the beginning of stay must be between 0 and L. The end of stay, it must be after the beginning of a stay. So it's between B and L, or infinity means that they did not go outside. T is between B and E, which means that they were infected in Wuhan, or infinity means that they're not infected. And the symptom onset can only occur after they were infected, and they can be infinity, which could be they are never infected or they just didn't show symptoms. Okay, so that defines support for these this random vector. The generative model we considered is based on this factorization of the distribution. So B and E is related to the traveling patterns of these people. So they will be either modeled or being conditioned on. What's more important is these two parts. This part is a distribution of transmission given exposure, and this part is the distribution of symptom given exposure and transmission. So I call this, we call this disease transmission and disease progression. So to allow extrapolation from just a selected subset of the data into the whole population, we're going to make two assumptions. The first assumption is that the disease transmission is independent of travel. So there is some underlying epidemic growth function that describes how likely you will be infected in Wuhan before its lockdown. And the second assumption is that the disease progression is also independent of travel, which basically says that the symptom onset needs to be greater than the time of transmission, and then it follows this incubation period distribution H. And then this mu is the proportion of people who showed symptoms, and 1 minus mu is the proportion of people who were asymptomatic throughout their course of illness. So the key assumption here, if you may notice, is that there's no B and E on the right-hand side. So this is assuming S is independent of B and E conditional on T. So if you are a graph person, it could be easier to understand this model through this graphical model, where the key assumption is that S is independent of B and E given T. And these variables, they are actually in a temporal or causal order if we think about this end of exposure, end of stay in Wuhan as the planned traveling date. So the idea is that the person first planned their stay in Wuhan, then they got transmitted, and then they showed symptoms. So the first assumption restricts the density of T given B and E, and the second assumption sets this there's this conditional independence. We also made two parametric assumptions to simplify the interpretation and the likelihood functions. I think this assumption 3 is quite reasonable. It simply just says before Wuhan's lockdown, the epidemic was growing exponentially. And there are these two parameters, kappa and r. R is the growth exponent that is very crucial in the analysis. And assumption 4 just makes a parametric assumption for the distribution of the incubation period. We assume it follows a gamma distribution. In the paper, we relax these assumptions in a Bayesian non-parametric analysis. But for the talk, I'll stick with these two assumptions. So the third thing I'm gonna describe is the sample selection that is happening here. So because we only observe cases exported from Wuhan, this set D is a subset of the original population P with 3 additional constraints. So the first constraint is that this time of transmission must be between B and E because we only use cases who contracted the virus. Second restriction is that the end of stay must be less than or equal to L, so they must leave Wuhan before the travel ban. And then the symptom onset time S must be less than infinity because we only consider those cases who were confirmed. And the vast majority of them have showed, they were confirmed because they first showed symptoms. Okay. So then following the basic principles, for statistical inference, we need to have a likelihood function. So for a moment, let's pretend the time of transmission T is observed and think about what likelihood function we can use. The naive choice is just the product of the joint density of the data. This assumes that we have IID observations from the Wuhan-exposed population, P, but that is not the case. We only have sample from this D. So that means that we need to, when constructing the likelihood function, we need to condition on this set D. So all it does is it divides the joint density by the probability that we observe these variables in this set D. So this is called the unconditional likelihood to differentiate with the conditional likelihood, where we're conditioned on the time of exposure, so condition on B and E, and we only use the conditional distribution of T and S given B and E. The reasoning is basically what the parameters we're interested in, which is the epidemic growth and the incubation period, they only appear in the conditional distribution of TS given B and E. So we could also condition on these sort of ancillary information. When we have unobserved time of transmission, we can either treat this T as a latent variable and use something like an EM algorithm, or we can directly integrate the likelihood over this unobserved T. So we would get a similar unconditional likelihood and a conditional likelihood by integrating over T. So the conditional likelihood will be less efficient than the unconditional likelihood because they do not use the information in B and E. So now B and E has some information because we don't observe this time of transmission T. However, if we use unconditional likelihood, the price we pay is that it will be less robust. So if we misspecify the distribution for B and E, then we will also get a biased estimate of the parameters. So in the paper, we actually derived the closed form likelihood function under the previous assumptions, under these two structural assumptions and two parametric assumptions. The exact formula is a little bit complicated. I'm not going through them, but I'll mention three things. First of all, this likelihood function does not depend on some nuisance parameters. It does not depend on this nu, that is the proportion of symptomatic cases, and it also does not depend on kappa, that is the baseline transmission rate. Second, when R is equal to 0, this is the likelihood function, and this has been derived earlier in this paper by Rich et al. In Statistics in Medicine. And for the unconditional likelihood function, you could also find it in the paper. So we applied this likelihood function to obtain point estimates of the parameters using maximum likelihood estimate. So the three parameters here are the doubling time of the epidemic and the median and 95% quantile of the incubation period. So they give another parameterization of the gamma distribution. And we tried using the same method, but on different subsets of the data in case some locations are more aggressive in testing and contact tracing and identified more COVID-19 cases than other locations. But the results are remarkably consistent. The doubling time is about 2 days, maybe a little bit more than 2 days. If you use all the locations, it gives us about 2.1 to 2.5 days. And this is much, much faster than what is estimated in by the naive method by fitting exponential growth. And the reason is that when we fitted the exponential growth model, we are implicitly assuming that the symptom onset has a marginal distribution that is growing exponentially. So this is actually reasonable if we had all the symptom onset time for the Wuhan-exposed population. So if we had observations from this P, if we have samples from this P, then we could use this exponential growth model. But however, our observations are from this set D, which are the exported cases. So for them, we did some theoretical calculations, and we found that a reasonable approximation for the transmission time is that it is growing exponentially, but also has a linear sort of decrease. So it's a multiplication of exponential growth and a linear decrease. And this linear decrease gives you the sort of the probability of leaving Wuhan when you are transmitted at time t, and the lockdown happens at time L. So through this, we can also derive a theoretical marginal distribution for the symptom onset, which has this form. So if you look at the actual distribution, marginal distribution of this symptom onset S of the Wuhan-exported cases, you see that there is an initial exponential growth period, but then it gets sort of, it hits this maximum around the time of the lockdown, and then it starts to decrease. And a few days before the lockdown, you can see that the exponential growth already slowed. And that is not because the epidemic was already contained. That's not obviously not the case. That is because people who were infected just a few days before the lockdown, we have a much smaller chance of leaving Wuhan and be observed in this data set. Okay, so if you actually fit this, our theoretical estimate to this marginal distribution of S using the MLE of these parameters, it actually provides a very nice fit to the marginal distribution of S. But if you simply fit exponential growth, you're gonna massively underestimate this growth of the epidemic. Okay. So for the incubation period estimates, I think I don't have time to go through it, so I'm gonna skip this part and see if I have any questions for me. If there are any questions for me in the Q&A.
Yes, we have a question from Georgia Papa de Georgiou, so I'm gonna unmute her.
Hi,
Georgia?
can you hear me?
Yes.
Hi, Georgia.
Hi, thank you. This is a great talk. I'm really enjoying it. So I think somebody already answered in the chat, but I might as well ask it here. Do you account for the fact that individuals within the same household might, be correlated? Whether you get it might depend on whether your spouse got it or your partner got it. And if you don't, do you know how perhaps we can accommodate that in the model?
We did address that at least implicitly. So one thing I did not go over for the interest of time was that the way we determined those exported cases, we only selected one case from each household. So if there's a cluster of cases, maybe there are a family who traveled from Wuhan to another place and several members of the family got confirmed, then we will only consider one case from that family with the sort of assumption that the others might have been infected outside of Wuhan by this first case who showed symptoms the first. It's not a perfect solution, and I honestly I've tried several criteria to sort of define the Wuhan-exported cases, and they all give us very similar results, especially for the doubling time. So that seems to be remarkably robust to however we define our cases. But for something like incubation period, I think obviously family, like who infected who, that's extremely important. And a better model could take that into account, but we didn't do that in our study.
Thank you. This is great.
So there's no more questions. Qingyuan, we have about 10 more minutes.
Okay, great.
Thanks.
All right. Yes, so I really want to move to the second sort of example in the talk. It's a much shorter example. It's hopefully I can cover it in 10 minutes. So this is about racial bias in policing. And this work is motivated by two very interesting articles, one by Knox et al. And one by Gabler et al. And the authors also had some very interesting and stimulating discussion online. And it appears that the authors from the first paper are more sort of, they tend to think causal inference problems with graphs. And the authors of the second paper, they use potential outcomes. And they had a very interesting discussion about whether you could assume some kind of ignorability condition in these problems. I'm not going to say a lot about their discussion. I think that's actually worth another online causal inference seminar. But what I will show you is a very clear evidence of selection bias in a naive analysis. So here is the setup in the first paper by Knox et al. So they considered 3 binary variables, D, M, and Y, where D is race and 1 means minority. M is a mediator, and in this case is police detainment. So you're stopped by the police. And Y is a binary variable that indicates police use of force. So Y equals to 1 means use of force. So the paper by Knox et al. Identified 2 key challenges in causal inference using in this problem. So the first problem is that we only observe data such that this mediator M, police detainment, is equal to 1 in the police administrative data. So, I mean, police are not going to record civilian encounters that did not even end in a detainment, because there's so many people that you encounter every day, right? So you cannot record everyone. So in this data, we only have those with M equals to 1. And the other challenging part is that it's can be easily conceived that there are some unmeasured confounders between the mediator M and Y, perhaps some kind of underlying racial disparity in the policing process. This is terrible news for causal inference, because the first challenge means that we will condition on M in the naive analysis. We will condition on M equals to 1. And the second challenge means that conditioning on M will open this path from D to M to U to Y. And this gives us collider bias. Okay. And the paper by Knox et al. Actually identified this collider bias in some influential studies. So the natural questions is, since we only have these kind of police admin data, what can we learn from it? So the paper by Knox et al. Considered 2 methods. So they denoted Y of D as the potential outcome for race D. And they derived some identification or partial identification results for these 2 causal quantities, which is just the average treatment effect, but conditioning on you're being detained by the police, or you're not only detained by the police, and but also you're a minority. So they call it ATE sub M equals to 1 and ATT sub M equals to 1. And their paper also provided some identification results for the average treatment effect. This is basically the effect of race on police brutality, police use of force. For these results, the key assumptions they use is include mandatory reporting, which says that if you're not stopped by the police, then you don't receive any use of force, which is a very natural assumption. And all police stops are recorded. And they also assume the treatment ignorability assumption that that the treatment D, this race, is independent of the other potential outcomes. And they, for the first partial identification result, they assumed mediator monotonicity, that there is bias against the minority in police detainment. But this is not needed for identify average treatment effect. So so building on their results, we obtained some additional results. The first thing we found was that these estimates that condition on the mediator being equals to 1, they can be difficult to interpret. So we even constructed some examples that these quantities, causal quantities, may have a different sign, even if the natural direct effect and natural indirect effects of the treatment D on Y have the same sign. So these sort of local causal estimates needs to be interpreted with a lot of caution. But our main result is actually about the average treatment effect. So the average treatment effect is not very easy to estimate because this is the identification formula. And to estimate this quantity, you actually need to have a sense of the probability of m equals to 1, given d equals to 1, and given d equals to 0. But this is very difficult to estimate because this is sort of among any police civilian encounters, how likely you are detained by the police. And there's basically no data for that kind of quantity. So one thing we realized is that if you simply consider a ratio of y1 and y0 instead of their difference, you could actually cancel this marginal probability of m equals to 1 using the Bayes formula. So we actually obtained identification formula for the causal risk ratio, which has two parts. The first part is a naive estimator of the risk ratio, which is just the ratio of the conditional expectation of y given d equals to 1 and divided by the conditional expectation of y given d equals 0 in this police admin data. So we condition on m equals to 1. And the second part is the selection bias factor that that sort of is related to the distribution of d given m and the marginal distribution in the population. So the idea is that we could estimate this marginal probability of the of d using some external surveys, for example, some population surveys. So we did analysis using these NYPD stop and frisk data for this naive estimator. And then we estimated this last quantity using some external surveys. So we did use two surveys. One is the current population survey. The other is the police public contact survey. What we found was that this selection bias factor is actually huge. If you don't use it, if you just use this first term, the estimated risk ratio is just above 1. So if you interpret this result, this only says that the minorities maybe they are a little bit discriminated against. They have slightly higher risk of getting police brutality. But if you actually consider this selection bias factor, the estimated risk ratio is huge. It's above 10. So there's a huge discrepancy if you ignore this selection bias. So let me summarize. So in this talk, I've given you two examples where there are ridiculously large selection bias. So these two examples, I mean, these selection bias, they occur if you analyze these topical problems in a naive way. And I think these are very important for our professions, whether you're a statistician, epidemiologist, social scientist, or data scientist, because they bring discredit on our professions. By that, I mean these sort of naive analysis, they produce an answer that I think if you actually just use your common sense to judge them, you will actually immediately tell that these are probably not correct. So in the COVID example, if the disease was only doubling in 6 to 7 days and corresponding to a R0 about 2.6, that means that it is not even more infectious than many other epidemic that didn't lead to a pandemic, for example. So that doesn't make sense. And I think if you ask a minority in New York City, they probably don't think they only have 30% more chance of being sort of being subject to violence by the police. But if these data analysis actually sort of keeps telling them these ridiculous suggestions or these ridiculous numbers, I think that's actually it's going to discredit us and our work. I mean, I deliberately choose these sort of very topical problems and sort of very naive analysis to show you how large the selection bias can be. The things are definitely much better in well-established research topics, but even over there, I don't think we can be complacent just because of the sort of the cost if we turn blind to selection bias. And the only solution I can think of, and I hope Louisa can tell me if there are any other solutions. But the only solution I can think of is we have to start from the first principles of doing the data analysis. Finally, the point I want to make is I think causal inference researchers are in a very unique and good position to identify selection bias. That hasn't been the focus of this field for a long time. But I think the way we're trained and the way we think about our research problems are very, very well suited for sort of thinking about selection bias, identifying them, and correcting them in real studies. And I think we need to act now. Okay, so that's it.
Fantastic. Thanks for the very nice talk, Qingyuan. We're now switching over to discussion. So we will have Louisa present some slides. After the discussion, Qingyuan, you will have the opportunity to respond. Okay, Louisa, whenever you're ready.
Okay, let me know if you can't see my slides. My name is Louisa Smith. I'm a doctoral candidate in epidemiology at Harvard, and I'm really thrilled to be talking about selection bias today. And I wanted to thank Qingyuan for a really great presentation and 2 really great papers, which I highly recommend you read. So I wanted to provide some food for thought by briefly discussing what we mean when we talk about selection bias. So we saw 2 examples in the presentation. One had to do with the estimation of the incubation period or the doubling time of coronavirus. And in the paper, Qingyuan and his co-authors go into more detail about how right truncation can lead to underestimation of this incubation period. The second example had to do with quantifying racial discrimination in policing. Here, the selection bias came from the fact that we only are able to use data that was collected administratively on the actual police encounters in order to estimate these racial disparities. One of the points that was brought up was the fact that selection bias seems underappreciated in our education, in our research, and I agree. And I wanted to talk about kind of one of the reasons why I think that might be, and some ways that I think we could kind of come to more common understanding and work on these problems. So one of the reasons why I think we have a hard time talking about selection bias is because we refer to a lot of distinct phenomena as selection bias. So Qingyuan brought up some points about model selection and how that can affect statistical inference. In certain fields, Confounding is sometimes referred to as selection bias because people are selected into treatment. We often refer to selection bias as problems of non-generalizability or non-transportability. And then we have a situation in which we have collider stratification in the language of DAGs, in which causal effects are biased even under the null. So I'm going to talk a little bit more about those last two in particular. But the other side of the coin, the other reason why I think it's hard to talk about selection bias is because we have all of these terms for it, as Qingyuan also brought up. These are just a few of them, and these have been developed in different fields in response to these different reasons for selection, depending on the topic area of interest. And I think sometimes we don't realize where there are similarities, and then sometimes we also don't realize where there are differences. So when I organize my thoughts about selection bias, this is how I like to kind of set up a framework to think about it. So the first type of selection bias I think about is selection bias when it comes to estimating descriptive measures. So when we're estimating the incubation period of coronavirus, as in the first example, that's an example of this. When we're trying to estimate things that are maybe will lead to people being less likely to participate in surveys, such as HIV prevalence or substance use, this can be another problem. And then, of course, another big 2020 selection bias example is political polling. There's a lot of selection bias in terms of who we can reach through things like random digit dialing or web polls, as well as people who are less likely to respond depending on who they're voting for. So although these are descriptive measures, they still require causal thinking. I liked Qingyuan's call to action for like returning to first principles. What is actually the structure of the selection and the data generating mechanism? So the second type of selection bias I think of is related, but now we're talking about causal effects and the fact that they don't always generalize to different populations. So one place that I see this in 2020 is when we're looking at something like results from a vaccine trial, and we ask, is this 95% effectiveness that we see in the trial participants, is that going to be what we see when we introduce this vaccine to other populations, say into an elderly population in a nursing home who are less likely to be part of the trial? And so this comes into play whenever we're introducing interventions to new populations. The extent of generalizability depends on the target population, not just on the sample. But luckily, we're okay under the sharp null of no effect on anyone. The third type of selection bias that I think of, which I think is the most interesting because it's often the least intuitive, are these examples of collider stratification bias, when we have selection bias even under the null. And so this was the structure that we saw in the racial discrimination in policing example. I have a couple other examples here that can be described by graphs in which we're either conditioning on a collider or a descendant of a collider. I'm not going to go into details on these examples due to lack of time. Excuse me. Oops. So there's a lot of really great work that's been done in the field of causal inference for characterizing these structures of selection bias that help us recognize and understand and react to selection bias, work on conditioning on colliders, on outcome-dependent sampling. and on general results for identification under selection. So I would argue that thinking about these structural forms of selection bias is really important, but I wouldn't discount these more canonical examples of selection bias, which teach us to recognize the forms that it can take in certain topic areas. So if you're working in pharmacoepidemiology, you're going to be more likely to recognize prevalent user bias. However, that can blind you to other forms of selection bias. So once we've recognized selection bias, which is kind of the first difficult step, what do we do about it? There are a number of options. Obviously, the best option is to avoid it in the first place, either by designing a study to not be subject to selection bias, or to collect better data, perhaps after the fact. So if we have a lot of attrition in a study, to track down at least some of those who are lost to follow-up. If we're interested in potentially extending our results to a wider population, measuring not only the effect modifiers in the study sample, but also in the target population. There are a variety of methods to correct for it, as Qingyuan showed us, by making various modeling assumptions. We can also use sensitivity analysis, which I'll talk about in just a second. And I think one option that's sometimes underappreciated is just redefining the question or redefining the estimand with a goal towards interpretability. I think this comes into play particularly in survival bias, when effects in survivors are not always particularly interpretable. So I know I'm going through these very quickly. I recently wrote a review that goes through some of these options. I wanted to briefly go into a little bit more, look a little bit more closely at the racial discrimination in policing example. So for this example, we see in this paper that we can write the average treatment effect on the relative scale as a risk ratio. And then under these assumptions, in particular, the assumption that force can't be used against somebody if they're not stopped by the police in the first place, then we can rewrite this causal quantity as a product of the observable estimand and then this selection bias factor, which consists of things that we can potentially estimate with outside data. So this selection bias factor we saw depends on this relationship between D, so D being the an indicator of whether you're a minority, and M, which is an indicator of whether you're stopped and apprehended by the police. And on a graph, that essentially boils down to this arrow. And we're able to do that because of this, I think, of this strong, but I think quite realistic assumption that when we set M to 0, there's no use of force. But in other situations, we may want to consider sensitivity analysis based on this unmeasured factor. So in this situation, that's some measure of racism, of increased suspicion towards minorities that affects both the probability of being stopped as well as the probability of using force. So this is something that I've done some work on with some collaborators, in which we've derived bounds for various estimands that may or may not be more useful or less useful in certain situations. So one of them is this causal risk ratio. There's also this causal risk ratio among the selected population. And I agree with Qingyuan that this is often a less interpretable estimand. And then the last one is a natural direct effect. So all of these bounds, which we can use for sensitivity analysis, directly rely on other relationships in this graph, and in particular, how strong this unmeasured factor is and its effects on the outcome, the mediator, or being selected into the study population. And they also, in certain cases, depend on the relationship between D and U once we condition on M. So depending on the situation, we may choose to try to approach selection bias and either correct for it or do sensitivity analysis for it, using data on kind of any of those nodes or relationships between those nodes. So my final thoughts are that I hope that we appreciate selection bias more in the future and have more than one lecture dedicated to it in our statistics or epidemiology classes. DAGs are important tools for this, as are stories about selection bias that can be very intuitive. Tools for correcting selection bias are really important, as well as for doing sensitivity analysis for a range of situations, because often we don't have the data or we don't have the knowledge about the data generating mechanisms to correct for it. But developing tools that rely on different assumptions or components of the distributions can be really helpful for different situations. So that's all I had. I wanted to provide some food for thought. Thank you.
Thanks for the nice discussion, Louisa. Qingyuan, do you want to respond quickly?
Just want to say thanks, Louisa, for the great discussion. I agree with everything you said, basically, and yeah, I think let's try to make more people aware of this, and I think causal inference researchers will have a unique place in this, and we should have more sessions like this, hopefully in some future conferences.
All right, great, thank you. So then I think it's time to wrap up. So first of all, let's thank Qingyuan for a really nice and interesting talk. Let's also thank you to Phyllis for helping out in Q&A, and thank you, Louisa, for the nice discussion. Next time, we're going to have a talk by Luke Miratrix, who will talk about using national data and meta-analysis techniques to get a handle on how bad some biases might be in practice. We're all looking forward to that talk. Until then, we hope you all stay safe and have a nice week. Thank you all for joining. See you next time. Bye.